Hello, everyone. Welcome to the ITS workshop on the spring 2022 semester. The main theme of this semester's workshop is quantum matter equations for open system quantum dynamics. And we are planning to have 3 different workshops this semester. The first of these will be dedicated to Polaron-based and other methods for intermediate and strong coupling regime. And we have 4 expert speakers for this workshop. We'll soon start without much introduction, but as a general guideline, so if you have questions during the talk, please send the chats to everyone. And then after the talk is over, I will collect all the host will collect all the questions. After that, if we still have some time, we'll have short questions until the time ends for each speaker, which will be 30 minutes. And then after the entire formal talk has ended, there will be informal discussion session. So please, if you have more questions or things to discuss, please don't go away. Okay, so with that, I'm happy to introduce our first speaker, Yuan-Chung Cheng from National Taiwan University. Okay, Yuan-Chung, why don't you show your slide and
okay, you see my slide?
Yeah.
Cool. So thank you very much for the introduction, and I really appreciate to have this opportunity to share with you about our research. Okay, so I'm trying to get this pointer stuff. Okay. So in National Taiwan University, our group work on developing methods to look into various electron transfer and exciton dynamics in in many different systems. I think for this audience, I don't have to go through on these topics here. And today's talk will be about how we develop methodologies to do this. But basically, in our research group, we have 3. We look at quantum dynamics in a model system-based Hamiltonian case. So basically, we have a system of electronic system and harmonic bass and system-based coupling. So everything here will actually detected by this electronic Hamiltonian and the spatial density. Once we have an electronic Hamiltonian spatial density, we should able to propagate the dynamics. But of course, this problem is not trivial, especially in the intermediate region where this electronic coupling and the best reorganization energy that dictates the system electron phonon coupling strengths are similar to each other. So you don't have a really small parameter to do perturbation up. And in that case, various theoretical methods have been developed to treat this dynamics. And I already see in the audience, there are many experts in this aspect, so I don't have to go into much details. In our research group, we have mainly developed perturbative methods because we want to study systems with large systems, and that requires to use a more numerically efficient approaches. And we have 3 different tools. One is based on a modified rate field theory. One is based on a small polaron theory. And more recently, we actually use developing another quantum Langevin equation approach. Okay, and these 3 methods actually have a different aspect of applicability. This modified rate field theory actually work on a pure diffraction electronic basis for exciton. So we focus on the electronic part of the system and treat the electronic diffraction dynamics exactly. Small polaron actually focus on the system base or electron phonon coupling. Okay, so it's based on a combined phonon electronic basis. Whereas in this quantum Langevin equation, it's based on a separation of this friction and fluctuation. So it actually is more suitable for vibronic dynamics. And today I'm going to talk about this coherent modified rate field and the small polaron approaches. In this coherent modified rate field theory, the basic is we treat the system in the electronic eigenbasis. So if in a exciton language, we transform this electronic Hamiltonian into an exciton state such that it's diagonal. And in doing so, your electron phonon coupling Hamiltonian will become off diagonal. It will become a complex operator. And what we do here is actually to put this diagonal fluctuation, diagonal electron phonon coupling into a zeroth order Hamiltonian, such that in the zeroth order Hamiltonian, we can treat the pure deflection dynamics and the electronic dynamics exactly. So this perturbation term only contains the off diagonal in the electron phonon coupling term. Okay, and this is a pure deflection representation, or so-called pure deflection reference system, turned by Grosov and Reckman. Okay, in an early paper. And this approach actually was developed by Jang and Munkmail in the late 90s, and then used by many people in the photosynthetic dynamics society. But then in that case, they only treat the population dynamics, so there is no electronic coherence. And what we do is we kind of extended this method, going through find a suitable projection operator approach to kind of have a full theory with coherent evolution, population transfer, and also the coherence deflection dynamics in there. Okay, and along this line, this generation of this modified refill approach actually was more recently developed by Thomas Rancher and Anton Tachinskin in recent years. And we have been using this approach as our workforce to treat many systems. We also find a representation to formulate this coherent modified refill theory into a generalized Limburg form that allows us to unravel the dynamics and have a quantum jump representation to propagate the dynamics. This could be useful for large systems. Now, we will apply this to a broad parameter regime. And you can see that at different electronic coupling, different electron phonon coupling strengths, you see that this CMRT fails at the strong system-based couplings, okay, and also strong electronic couplings. So in this regime, it's not very good, and this is basically due to this pure representation does not take care of this electron phonon coupling very seriously. Now, in order to have a good judgment or a good idea of whether or not this method is applicable, we develop accuracy criteria, okay, based on the square fluctuation of the system-based coupling term, and we can actually analytically find the approximate result, and this allows us to define the applicability of this method. So if this value is greater than 1, this line here, then in this regime it's not very good, but in those regimes they are good. So you see that this CMRT actually works in a large parameter regime for various bias. Okay, and we apply this to treat FMO dynamics compared to numerical exact hierarchy equation or motion approaches. You see that the results are actually in good agreement. We can also apply this method, simple enough. We can apply it to a 42 chromophore LSC2 compress to simulate dynamics after a laser excitation. So we see those coherent dynamics due to laser coherences can be simulated with our coherent modified refill theory. And the result also fits the absorption spectrum quite well. And this allows us to find energy flow diagram for this LSC2 dynamics. So this actually tells us everything about this energy transfer within this complex. Okay. More complex system complex such as this photo system 2 core complex can also be modeled by our method. Okay, we built effect Hamiltonian for this model, and we use the CMRT approach to propagate the dynamics, and also then came up with this energy flow diagram. This again allows us to fully elucidate energy transfer dynamics in this system. Okay, and identify energy transfer hotspots, core fields that are important for bridging energy transfer from one group of the core field to another group. Now we are actually building a model for the 300 core field photosystem 2 supercomplex, and we want to simulate dynamics such as when this complex is excited, how energy flow goes to the reaction center. Okay, some preliminary result actually shows that this model can be built to have or to exhibit a similar quantum yield that is in agreement with experimental observations. Okay. So pretty much this CMRT is this approach we use to model photosynthetic complexes with reasonable amount of success. On the other hand, we also develop, or we also are interested in small polaron quantum mass equation approach. This is based on a small polaron basis. So polaron, the idea of polaron actually has a long-standing history in condensed matter physics. Was first developed in 1946, but then of course everybody knows that Landau also picked up this idea and developed many new approaches. And basically, this is the idea of polaron. If you have an excitation at some place, it will deform its surroundings. And when it moves, the surrounding will move with it. Okay. And this idea has been extended to many other systems, not just electron, also excitation and many different systems. Okay. So in the so-called small polaron representation, or in a polaron representation, the basic idea is excitation will deform its surrounding. And when this excitation moves, the surrounding should move, this deformation should move with it. Okay. And this phenomenon is called dynamical localization. It's a dynamical phenomenon. And if this system, this localization or deformation is in its full extent, we call this a small polaron picture. Okay. And mathematically, we can achieve this small polaron picture using a small polaron transformation. It's a unitary transformation that depends on the site. When the site is excited, you have this displacement operator applied onto it. So this transformation allows you going from original basis to a displaced basis, and we will call this small polaron basis. It's been used by many researchers. I see several in the audience here, so I don't have to go through these things. So after polaron transformation, we have this transformed small polaron Hamiltonian that exhibit a Lagrangian entry and addressed or renormalized electronic coupling term, and then a new system-based coupling that actually is the off-diagonal renormalized electronic coupling around its mean. Okay, so does it work? Actually, earlier calculation that we did to look at the Hausdorff model, one-dimensional Hausdorff model, and here we plot the inverse effective mass as a function of electron-phonon coupling G, and you can see that the strong coupling perturbation theory and the weak coupling perturbation theory both failed at its opposite limit. However, this small polaron approach actually interpolates between strong, weak, and the strong coupling. So it works well, reasonably in the intermediate coupling regime. And the good quality comes from that this transformed effective coupling actually has a temperature and coupling strength dependence. At large electron-phonon coupling strength and the high temperature, this J goes to 0. So it have a coherent to incoherent transition built into its zeroth order Hamiltonian. Also, this stress system-based coupling term actually is a fluctuation around the average coupling. Already depicts that if you have an electron transition from J to I, then this phonon cloud at the J side will be destroyed and another phonon cloud at the I side will be created. This means this electron and the phonon will move together. Okay, so the dynamics, the polaron dynamics is in this coupling. Now, if we use this coupling, crank it through this generalized quantum mass equation approach formalism, we get a small polaron quantum mass equation approach. Okay, so this was published with Seogjoo in 2008, Reckman and Joe. And now we actually compare this with SPQN approach with similar FMO dynamics. We'll compare it with this reduced hierarchy equation approach. The agreement is quite well. And we also look into this rate calculated in this small polaron theory. we identify that the rate actually have two contributions, one coherent turn and incoherent turn and one coherent turn. Okay, so they have a different temperature dependence, and they have they dominate different parameter regime. So we can use this to plot rate as a function of temperature and the electron phonon coupling strength, and identify different regions of the dynamics. For example, only in this very low temperature region, then this coherence term play important role. In that case, and temperature increases, the rate actually decreases. And then you have in this region, this hopping turn dominates. And in this case, in temperature increases, the rate increases. And in this region, you have this trapping case. When temperature is very high, coupling is very strong, the exciton will be trapped. Okay. So we also, for this SPQME approach, we also benchmark in a broad parameter regimes, different system-based coupling, different electronic coupling, and we see that this method fails at strong electronic coupling and the weak system-based coupling. Okay, and a lot of this is because at a strong electronic coupling, the response of the bass does not is not fast enough. So this small polaron, fully dressed small polaron approach is invalid in this regime. And many researchers such as Ahsan here already demonstrate that this can be resolved by a variational polaron approach. Okay. And again, we look at the accuracy criteria of this method, and we also come up with a simple expression that tells us how good this is. Okay, when it's smaller than 1, then this perturbation approach worked. And this is the two the accuracy parameter for different electron coupling and different electron phonon coupling. Okay, at a higher this is at a lower temperature and at a higher temperature. And no, sorry, this is a large energy gap bias and smaller energy gap. Okay, you can see that when energy gap gets smaller, this applicable regime becomes smaller, and this is because when in this case the excitation is more localized, this is more delocalized, and delocalization or excitation actually effectively decrease the electron phonon coupling and makes this small polaron approach less applicable. Okay, so one interesting thing here is if we compare the accuracy criteria for CMRT and the SPQME, you can see that they work in different regions. Okay, so they are complementary to each other. They represent different representations of quantum dynamics. Okay, and this allows us to identify at which regime we should use which theory, and allow us to kind of stitch the two theory together to have a complete a method that actually works in all the parameter regime. Okay. And then I see that this section is about Polaron-based and other methods for intermediate strong coupling regime stuff. And I just give you a general, kind of a general overview of things. And two interesting things about this Polaron approach I want to mention here. I don't have much time, so I'll go through this quickly. Okay. So one is about highly non-equilibrium electronic dynamics during Polaron formation. Okay, and I say that this is about a jailbreak of excitation before window closed. And this is actually a regime at this area when this electronic coupling and the system-based coupling are both strong. Interesting dynamics. And the other one, I call it duct tape, the slow-mo problem using furthermore approximation. Okay, so this gives rise to a frequency-dependent variational ansatz that we found quite useful in solving this slow mode problem in Polaron. Okay, so I mentioned about this inhomogeneous term. And this inhomogeneous term in the small Polaron quantum master equation actually represents dynamics. It depends only on the initial condition. That's why it's called inhomogeneous term. It represents the electronic dynamics during Polaron formation. So Polaron formation takes time. And during this Polaron formation, electrons have a chance to tunneling to the other end. Okay, so if you want look at the electron transfer from a donor to an acceptor during this Polaron formation time, something can happen, and this is described by this inhomogeneous term. So if you look at the inhomogeneous term, okay, the amplitude could be significant. Even for a parameter, this is a bias, small bias, J electron coupling is 1, the electron form coupling is 0.5, beta is 1. So this is some kind of a normal or not strange parameter region. You can see significant inhomogeneous term contribution. Okay, and this gives rise to an important non-Markovian contribution to the dynamics. So I'm sorry, this should, okay. This box should come after I look at these pictures. Okay, that's for the sake of saving the time. So because of this inhomogeneous term, when you consider inhomogeneous term or without inhomogeneous term, at the broad parameter region at low temperature, this is when temperature is low, you see that the inhomogeneous term actually contribute a lot to the dynamics. At a special case, in this case, this large electron coupling and large electron photon coupling, actually the inhomogeneous term changes the dynamics totally. Okay, and the dynamics shows a biphasic behavior because initially this inhomogeneous term is a tunneling during polaron formation before trapping. But after, when polaron actually formed, this trapping forbids or does not allow the polaron to transfer effectively because this very weak Frank-Condon overlap between the two polaron states. Okay, so such early time electron transfer dynamics represent a hard carrier transport scenario and could play important roles in those dye-sensitized solar cell or organic solar cells. For example, in some dye-sensitized solar cell, experimental result tells us that the electron injection dynamics is ultra fast, 100 femtosecond. However, the quantum yield is very small, and this kind of dynamics might play a role in this. Okay, but at higher temperature, this is quite high temperature. This effect is smaller because the coherence has been destroyed, so you don't get to tunnel that effective. This also depends on the energy gap bias of the two sides. Okay, and you see that there is a non-trivial maximum at some specific bias. This is kind of similar related to this Marcus theory stuff. Okay, it has to do with this regression energy of the system. So that's quite interesting. And then another story I want to tell you, and here quickly actually, is we know that this small polaron theory divergence, or it's not useful when you have an omega spatial density because this 1/omega² factor in this integral. Okay, so if you have this kind of Drew-Lorentzian spatial density, you cannot use small polaron approach. People have been attributing this to this time scale problem because sluggish mode cannot accommodate or cannot go with this excitation. So this divergence in the small frequency means that you cannot use small polaron to describe those slow modes. Okay, there are various solutions. Okay, some people here already did it, but we took this idea from Ruckman co-workers. That's if we can split the spatial density into high frequency and low frequency modes, and if we do so with a suitable function and treat the low frequency mode semi-classically and high frequency mode using small polaron theory, we might find a way to make this work. Okay, but the question is, how do we determine this splitting frequency? How do we separate these two? And we apply a variational approach to do this. So we use a variational transformation, and then apply this Bogoliubov's bond to determine where we want to split this. Okay, and we have an expression for this so-called splitting frequency. And every mode that has a frequency higher than this, we apply small polaron transformation. For modes that is lower than this, we do not just and treat this semi-classically. We apply a Wigner transformation to it. Okay, and we think this is a kind of a more frequency-dependent variational answer for polaron transformation. Yeah, and I'll skip this. Okay, so this allows us to rewrite the small polaron Hamiltonian into some classical, semi-classical energy differences, and this is just static Gaussian energy disorder. Actually, recommend or Bobek use semi-classical dynamics to propagate this, and we just freeze all the modes, so they become static, and then we call this frozen mode small polaron quantum method equation. Okay. And this actually works quite well for in parameter regime, and originally this polaron is already good. It improved the polaron result a little bit. This is blue line FM SPQME. And in a regime where small polaron approach failed, this large J, actually it works much better. Okay. And then we can also apply this to a system with ohmic bass. And this is the situation. We intentionally use a very weak kind of very weak electron, very weak system-based coupling here, so that we can compare this to red field. Okay. And we use a dynamics with very small splitting frequency, so this is close to small polaron dynamics. And we see that the small polaron fails, but the furthermore actually works well. Okay. So this significantly expands the applicable regime of the small polaron approach. And we think that this thinking of a frequency-dependent variational polaron approach, where you address the high frequency mode but keep the low frequency mode undressed, could be a good approach to push on this polaron method. Okay, I don't need to go through this, but I want to emphasize that this polaron representation actually are very fun to work with. Okay, and I want to thank my students and the funding agencies here for their support, and I thank you for your attention.
Thank you so much. Let me quickly go through questions Eitan Geva asked about the model parameterization for photosynthetic systems, and also whether you are using the QME for time local or non-local form, and also for the Polaron based methods. The question is whether they can be generalized to unharmonic non-condensed couplings. And then Arif Yula asked whether these Hamiltonian methods can be applied to excited state dynamics of real molecules. And finally, Kai Liu asked why the volume of free energy a good measure.
Okay.
Yeah.
Okay, I'll go. I'll go through this. Okay. So we actually, there's another story that we actually developed methods to parameterize those Hamiltonians. Okay. So, but we found we examined different methods, but the best approach that we found is this semi-classical approach by Thomas Renger, and use this basically electrostatic embedding of loss chromophores. That works the best. Okay, but you always need to tune a little bit and compare to experiments. So there's a lot of space to work on in that. Okay, and the QME we use is time local because it's easier to propagate. Okay. And for generalizing this method to general Hamiltonian, including anharmonic potential surface and non-constant couplings, it's possible, but it could be more complicated. I can imagine that in this so that's why we developed this Langevin equation approach, because in the Langevin equation approach, you can pretty much use just friction to treat this kind of non-equilibrium dynamics, and it's very easy, or it's much easier to work with web packet propagation in that representation. So we developed this Langevin equation approach specifically to treat system when the potential energy surfaces are important. You need to look at the specific potential surface.
So just as a clarification,
yeah,
it isn't the small. So you're saying that the small polaron and modified red field trick can be used beyond, okay, harmonic spin boson like Hamiltonians?
Well, it's possible, but it will be difficult. For example, Buffy and Mount, they look at systems with higher order couplings, square nonlinear couplings. Okay, so if you have an harmonic potential, in principle, you can parameterize that into a non-linear coupling term in your treatment, right? And you can still apply this, but then you have to use a different form of this unitary transformation. Okay, so it will be very complicated, and I don't recommend doing so.
So it wasn't done yet, okay? But
No. Yeah, I think it's possible. Yes. Okay. And
how about the free energy for the variational?
Free energy for the
Vogel-Lyubov free energy. Why is it good measure? Yeah.
Well, actually, it's the simplest measure that we can use. I tried different free energy approaches or different variational approaches. This is the easiest to implement. And if you are interested, you can look at the KG Lindenberg's early publication in the late 90s and early 2000s. They have applied a series, many variational approaches to this problem, and that it's actually well tested. Okay.
Okay. Yeah. Thank you. Ahsan actually asked a question, but he's a second speaker. So why don't Yuan-Chung, you stop sharing yours? Yeah. And Ahsan, you can share yours, and then you ask question if you want.
Hey. Yeah, I guess I'm using up my own time here by asking a question, but I'm just wondering if you'd compared the frozen mode variational approach to the more standard variational master equation, and whether they're similar or whether there are differences between the two.
There will be differences, I'm sure. And I believe that if you use a proper ansatz and go through this variational, it will work better than this frozen mode approach, because we made extra approximations in this frozen mode approach. So your method will work better.
I
don't know.
Okay. Yeah. I think we can have more extended discussion during the informal discussion session. So let me introduce our second speaker, Ahsan Nazir. He is from University of Manchester. Yeah, here is his presentation. Yeah, thank you.
Can everyone see the slideshow okay?
Yes.
Good. So, well, thank you very much first to Seogjoo and Eitan for the invitation to speak today. I'm going to say a bit about some work that's actually ongoing work at the moment. So these are fairly preliminary results, but hopefully they'll be of interest. Sorry, I keep on changing slide by mistake. Hopefully they'll be of interest to the audience. So what I'm going to talk about is actually work statistics. So that's the statistics of work in a driven quantum system that's adiabatically driven. So it's driven slowly, which helps with dealing with the time dependence. But it's strongly coupled to a reservoir, so a heat reservoir. And we'll treat the strong coupling through a Polaron method. And this is primarily work that's been done in my group by a PhD student, Owen Dibber, and also Harry Miller, who's a postdoc in my group as well. Okay, so just to outline, I'll start by describing the two-point measurement protocol for work, from which we can access a probability distribution for work in a time-dependent quantum system, and we'll analyze that using a characteristic function, which is essentially a Fourier transform of the work probability distribution, and that leads us to formulating a master equation approach in terms of the counting statistics of work in the system. I'll then talk a bit about how we deal with the adiabatic dynamics, deriving an adiabatic master equation, where we also track the counting statistics. And then we've already heard a bit about how the Polaron approach works, but I'll just recap a little bit about how we move beyond weak coupling by using the Polaron transformation. Why do we use Polaron in this particular case? Well, it's because we're actually interested in a particular physical system, which is a classically driven quantum dot, so periodically driven solid state system, where the Polaron approach is well suited to modeling the exciton-phonon interactions that occur in such systems. And then finally, I'll show some preliminary results where we compare the work counting statistics of a weak coupling approach and a Polaron approach. So in order to characterize the stochastic work in our system, we employ this two-point measurement protocol. So we imagine that at some initial time, there's some projective energy measurement that's performed importantly on the combined system and environment. And the reason for this is that, that although the system itself that we're interested in is open, the combined system and environment is closed, and so it evolves unitarily. So if we then make another energy measurement at some later time, we can associate the energetic changes with work under the unitary evolution. So that's what I mean. Whether that such a measurement is practically possible is obviously another question, but from the point of view of working out the counting statistics, this is a useful approach to characterize work in terms of the unitary closed evolution of system plus environment. So there are two projective measurements, one at time 0 and one at time t, unitary evolution of the combined system and environment in between, where we have some system Hamiltonian that's time dependent, some Bath Hamiltonian that we assume is static in this case, and an interaction Hamiltonian. Actually in the examples, I'll show the interaction Hamiltonian is also static. It doesn't change in time, but in principle, we could turn interactions on and off if we wanted to. Actually, just as an aside, I won't talk about heat counting statistics in this talk, but of course we could characterize heat in a very similar manner by just considering projective measurements performed only on the static environment rather than the full system and environment. Of course, there we're assuming a definition of heat, that the internal energy of the bath is the correct definition of heat, even in the strong coupling regime, and that may or may not be the right definition that we want to take. I mean, we could imagine that the other definitions of heat may be more appropriate as well. But as I said, we're going to focus on work for this presentation. So by taking these two projective measurements, we can define a work probability density. So we have an initial measurement. So this capital pi n is some projection operator onto energy eigenstates of the combined system plus bath. And so the probability of getting some outcome n is just given by a trace of that projector with the initial density operator of the system and bath. Then at some later time, we have some conditional probability of getting outcome m when we make our second measurement at time t, given that we got outcome n in the first measurement. And then an expression can be derived straightforwardly for what that probability is in terms of the projectors on n and the projectors on m, and the unitary time evolution of the system plus bath in between. So obviously this is not a straightforward thing to calculate at all exactly, because we've got the full time evolution of system plus bath, but this is what we're going to end up approximating with the Polaron approach. The work done on the system is then the measured energy difference, and so that leads to a work probability density definition as given in the red box here. So it's the sum overall of the probabilities with delta functions for the work at the actual energies that are the difference in actual energies that are obtained at time t and time 0. Now, for practical purposes, actually, it's a lot easier to work with the characteristic function than directly with the work probability density. The characteristic function is defined as in the slide here, and it's essentially a Fourier transform over the work probability. It contains all the same statistical information about the work performed on the closed system and environment as the probability density itself. And for example, moments of the work can be obtained from successive higher order derivatives of the characteristic function, where we evaluate the characteristic function at chi equals 0. Actually, what's very useful for our purposes and what allows us to use a master equation approach, and in particular a Polaron master equation approach, is that the characteristic function can be written in terms of a counting field dependent density operator. So if we consider chi in the characteristic function definition in terms of the Fourier transform as being our counting field, then we can write the characteristic function as a trace over some generalized density operator that depends also on chi. So then that becomes obviously a trace over just the system of the trace over the bath, so the reduced counting field dependent density operator, which is what we're going to look to approximate. Notice that because this is a trace, I can insert Polaron transformation into the trace. And by using the cyclic property of the trace, I'll find that it doesn't change the definition of the characteristic function. So the characteristic function itself is unchanged by inserting that Polaron transformation into the trace, but it allows us to form a different perturbation theory than the standard weak coupling theory. So we can access, as we heard in the previous talk, different regimes of system bath interaction strength and temperature actually as well. So the counting field dependent density operator obeys an equation of motion that looks a bit like the Liouville von Neumann equation, but slightly different because this counting field dependent Hamiltonian is evaluated at the negative of chi as well as at the positive values of chi. And the transformed Hamiltonian itself has this form. So it's the original time-dependent Hamiltonian plus an extra term that depends on the derivatives of exponentiated operators with the Hamiltonian at time t. Now, obviously, this is a difficult thing to work with because it's the full Hamiltonian at time t. Remember, we're making measurements on the interacting system plus bath, so the combined system and environment. But again, we'll approximate this in the Polaron frame as simply just the system plus bath Hamiltonian in the Polaron frame, assuming that the interaction in the Polaron frame provides only a small correction to the energy values that are obtained. So when we trace over the bath, the reduced counting field dependent density operator obeys a generalized master equation with some Liouvillean that depends on the counting field. And of course, the form of that Liouvillean depends on what approximations we make in deriving the master equation. So a standard approximation would be the weak system bath coupling approximation, which we're going to look to move beyond, but also the time dependence will enter the master equation as well through the time dependent Hamiltonian. And we're going to assume slow time dependence here, so adiabatic dynamics. Yeah, so dealing with arbitrary time dependence is generally difficult or can be difficult. So let us, for the purposes of this talk, just consider the adiabatic limit of slow external driving. And as I said earlier, the interaction Hamiltonian will be kept static. So following the method put forward by Albach and colleagues, we derive a Markovian Lindblad master equation under the Born-Markov and secular approximations. So this has the standard kind of form that we would associate with a Lindblad master equation, except now the shift terms, so the Lamb shift terms, become time dependent, as does the dissipator. And the time dependence of the dissipator is not just through the time dependence of the rates, but also through the time dependence of the Lindblad operators themselves that are changing in time to follow the adiabatic basis of the system. So this is for a standard master equation, but we can apply the same approximations to the counting field dependent density operator, and then we will end up with a master equation for the counting field dependent density operator that's valid for adiabatic time evolution, as I've shown at the bottom of the slide here. So I mentioned that we want to move beyond weak coupling, and one motivation for this is to look at solid state quantum optical systems. So the system I have in mind here is a semiconductor quantum dot that we'll treat as an artificial atom, so just a two-level system for our purposes. Here in this schematic, it's confined within some micropillar cavity, but just think of that as a way for light to enter and to be observed in a emission, so reflection, for example. The cavity is not strongly coupled to the dot here, so we don't treat it explicitly, although such a treatment could be done if necessary. How this kind of setup is different to sort of textbook quantum optics is that we also have strong interactions with the surrounding lattice vibrations. So the solid state system is important itself. So we need to model those exciton phonon interactions in such a system. So to the model itself, we have a two-level system, a ground and then excited state, where we can coherently drive Rabi oscillations between the two with some Rabi frequency omega due to some external classical laser field. And the oscillations will be damped by phonon interactions. So we've got this typical Hamiltonian where we've got some two-level system with some driving that we're going to treat within the rotating wave approximation, which is well justified close to resonant driving for optical frequencies. And then we've got a bath of harmonic oscillators, which is our phonons that couples linearly to our two-level system. We've seen a schematic picture like this in the previous talk, but this is just illustrating again the polaron idea for these kind of systems. So as we're driving our two-level system with some Rabi frequency omega, the lattice displaces in response to changes of the charge configuration. So we're exciting an electron from the valence to the conduction band and vice versa as we drive these oscillations. And so this then causes it as a displacement in the lattice, and this is essentially the polaron formation within our system, or at least the dynamic polaron formation. So then we have a new boundary between what we consider to be system and environment. So we perturb around this stressed state of the system with the bath displacements instead. So we incorporate this into our master equation through the polaron unitary transformation, and it allows strong electron phonon interactions to be considered. We can actually compare this with experiments directly. So here we can see in some for emission, essentially these are interference fringes from emission from a quantum dot, and this drop in fringe contrast on short timescales is the polaron effect here in this system. So you can see that the polaron master equation captures that very well, where a more phenomenological pure dephasing master equation completely misses that polaron formation effect. It also gives rise to a sideband in the spectrum that wouldn't be captured without this polaron feature. Well, also we can see temperature dependence, for example, in resonance fluorescence, which is again due to the system phonon interactions. So in a little bit more detail, here's the unitary polaron transformation again. So we apply that to our Hamiltonian to identify a new perturbation term. What we do is we perturb around the kind of average of the new interaction Hamiltonian, and when we incorporate that average into the system Hamiltonian, we end up with a renormalized version of the system driving. So this factor kappa is the polaron renormalization, and it reduces the driving strength. So kappa lies somewhere between 0 and 1, depending on how strong the interaction is and how high the temperature is. The system now couples through raising and lowering operators rather than through sigma z to environmental displacements rather than to the linear coupling form that we had previously. And following the same adiabatic Markovian procedure, but importantly in the polaron frame now, we can then obtain a generalized polaron master equation for the counting field dependent density operator. So here's some preliminary results showing a weak coupling and polaron comparison for the full probability distribution of an example system where we've taken a superohmic type spectral density, which is appropriate for acoustic phonons in quantum dot systems. We're assuming here that we drive the system, on some time scale until it reaches a steady state, and then the first measurement, so the t=0 measurement, is actually made in the steady state. That pushes the system out of equilibrium, and then the second measurement is made an integer number of driving periods later. What we're showing here is the probabilities, which are discrete for the differences in energy measurements. So the work probabilities for different coupling strengths. So alpha equals 0.01, the weakest coupling strength, and polaron is circles, and weak coupling approaches squares. And you can see that the polaron weak coupling approaches agree there, or pretty much agree. But as we increase the coupling strength, we see they start to diverge from each other. Interestingly, one thing we see is that there are more work values predicted from the polaron master equation than there are from the weak coupling master equation. And that's because of the renormalization that I said of the driving term that reduces the driving term in comparison to the bare driving that is treated in the weak coupling master equation. We can also see that the polaron distribution seems a little bit more symmetric than the weak coupling distribution here. Something else I just want to highlight is that we can include Lamb shifts, or we can neglect them, which is sometimes done in the literature. What we find here, so the red filled circles, polaron predictions for a particular coupling strength without Lamb shifts, and the empty circle is with the Lamb shift, and likewise filled squares are weak coupling without the shifts, and empty squares are weak coupling with the shifts. And what we find is that the shifts are much less significant in the polaron treatment. And part of the reason is that we've already incorporated a lot of the weak coupling shift by the polaron transformation and the renormalization, as I said, in the system Hamiltonian. So the residual shifts that are left over are much smaller than they are in the weak coupling approach, which is also trying to approximate as best it can this renormalization of the system energy scales through the Lamb shift in this case. So I'll finish there, I think, and just to summarize, I've talked a bit about how we can calculate things like the adiabatic work probability distribution for a driven quantum system beyond weak coupling by using the polaron approach. There's a number of future directions that we're interested in looking at. So we want to think a bit more about how we probe these work distributions experimentally, for example, with a driven quantum dot system. I'm looking now at extensions to non-adiabatic periodically driven systems where we can maybe make a rotating wave approximation within the generalized master equation to remove the time dependence in a particular representation there. I'd also like to look at other procedures such as these shortcuts to adiabaticity that keep you along the adiabatic path in finite time. And something I've not talked about at all today, but I've done a lot of work over the past few years on a different approach to strong coupling called the reaction coordinate master equation. And we'd like to try and incorporate those sort of approaches into calculating these kind of probability distributions for work and heat as well. So I'll just leave up the acknowledgements and say thanks very much for your attention.
Thank you. So we have two questions. One, actually, Eitan asked a lot of questions. For example, the assumption of the adiabaticity, does it mean it's reversible or not? So whether your work can be generalized to irreversible work. in relation to that, also he is also asking, so the distribution of energies rather than a well-defined work, is it because it's microscopic or not? So I think you can answer his question based on the chat. Now another question by Micheline Solly is about the polaron, the dispersion at long time limit, whether it's actually artifact of measurement, whether the experimental data are really physical, and also what drives a closer agreement between theoretical and experimental data at short times. And Yuan-Chung also asks about, commented about, I think a general polaron approach. So, Ahsan, why don't you answer those questions? Yeah.
Okay, there are quite a few
yeah.
questions.
You can take a look at the chat. Yeah.
Yeah. So the first one is about adiabatic processes. So if we want to generalize beyond adiabatic processes, we need a way of treating time dependence within the master equation formalism that's consistent with the approximations that we make. So the reason that we're looking at slow driving here is that there's a procedure, an established procedure that we can use that's still consistent with things like the Born-Markov approximations, which is what we make in the Polaron frame. Of course, that's not the same as making the Born-Markov approximations in the original frame, but it still limits how fast driving we can consider. So what we have to what we would have to do is have a more general approach to the time dependence, which such approaches do exist. And for example, for periodically driven systems, we could look at Floquet type approaches as well. But for this, for getting started with looking at these kind of probability distributions, we decided that the slow driving regime was probably the most straightforward way to go.
Would you agree that this is reversible work because of that?
How are you defining the reversible work in this? I mean, there's both work and heat
reversible
going on
is
here.
usually ultra slow processes, right?
Yeah,
I mean,
it's not completely reversible in the sense that we have loss of heat, but it's probably the most. It's probably the limit where we either do the least work or we get the most work.
You can have heat in a reversible process. Okay.
Well, I would say that this is still driven from thermodynamic point of view. So it is actually open-driven situation, but the adiabaticity is with respect to quantum dynamics. So I think it's kind of
it's not necessarily thermodynamically adiabatic in that sense.
Okay, we can talk about this later.
Yeah, so do you mean, does it thermalize at every point along the trajectory? Yes. I guess. No, I don't think it does. It's driven out of equilibrium, I think, here.
How is using those basically laser fields, okay, in the model?
Yeah, I think this is actually will be more extended question that involves quantum thermodynamics. So I think probably we should discuss about it later.
Okay, the slow driving one. Yeah, we have to be careful about the slow driving. There's only that's why I said it was preliminary results. There's only very particular driving regimes where that can be applied. And so that's why more generally I want to look at this rotating wave approach that doesn't limit us to adiabatic systems.
Yeah, we wrote papers many years ago about this. I don't know if you are familiar.
Yeah. Okay. So how about Ahsan answers to Micheline Solly's question about the agreement between theory and experimental data at short time?
So was it to do? I wasn't sure exactly what the question was referring to there. Was that this?
When you showed the agreement with the experimental data, your I think 2019 paper, PRL paper.
Yeah.
Yeah. So the question appeared at that time.
Okay. So fundamentally, I'm not sure that there's anything particular. I think, you know, the longer the time scale here, the more that there are other kind of fluctuations that come into play that are probably not included in the model, which is why the points seem to be a little bit more dispersed around the theoretical line at longer times. But these will be sort of small effects that are beyond what we considered in the model itself, I think.
Okay. And also Yuan-Chung Cheng also asked about, so in your case, the driving operator is also modified by the Polaron transformation. Can you elaborate on how it is treated?
Is the driving operator?
Yeah.
So because it's classical driving, it's straightforward. If it were a quantum field, it would be much more complicated, because then we'd have operators that would be system, displacement, and electromagnetic field all producted together, playing a role. And so I would agree, for quantum light interactions, it would be a difficult calculation. But for the classical driving, it's much more straightforward. We just get this renormalization of the driving term.
Okay, thank you. Yeah, so thank you for the talk, Ahsan, one more time.
Thanks.
Now, Eitan Geva will be host for the remaining two talks. Eitan, why don't you unmute yourself?
Okay, thank you, Sugi. And we are going to start the third lecture. So the third lecture is by Jianshu Cao from MIT, about Polaron master equation approach for non-equilibrium quantum processes.
Well, thank you. Can you hear me? I'll see my slides. Okay. I'd like to thank Sagi and Eitan for the wonderful workshop. So my talk will be on a non-equilibrium version of the quantum transport, the Polaron approach to quantum transport. So I started with a brief introduction, then discuss the calculation of heat transfer. Then I extend to other applications and also limitations of the Polaron approach. So this is an overview of the other projects in my group. We are working on the methods for condensed phase systems. I will mention briefly, because this is a quantum mass equation workshop. For quite a few years, we've been working on the quantum dynamics in light harvesting systems and organic semiconductors. Now, recently, we've been focusing on the strong light matter interaction, particularly the Floer-Quid theory and the cavity QED. Now, this talk, I will focus on the non-equilibrium quantum process. So as I mentioned, I want to mention briefly about our work on the quantum dynamics, because a lot of interests in this area. The first method is called transfer tensor method, that allows to take the short time dynamics and extrapolate to long time dynamics. And the method is completely general. It can be applied to quantum mass equation, but also quantum simulations, can be applied to classical or quantum. It essentially is a black box method to processing classical or quantum dynamics. I have several papers, including a joint paper with Eitan. The second method we've been working on is the stochastic quantum dynamics. And this is based on a very simple idea that system-based coupling in general can be expressed in the product form. And for any product we can deconvolute with a stochastic field. So in this way, we can deconvolute the system and the bath. As a result, we have a stochastic Lewinian equation. And this equation is completely general because we can treat bosonic bath, fermionic bath, spin bath, anharmonic bath on the same footing. And using this starting point, we can derive the most generalized version, most general version of the quantum mass equations. We can also use this as a starting point for stochastic simulations or hybrid simulations. So these are some of the papers. So now I'm going to talk about the Polaron approach. We started with the thermal equilibrium. From the classical statistical mechanics, we know that when a system is perturbed weakly by the environment, it always assumes Boltzmann. Now, this statement breaks down in quantum mechanics at a low temperature, because even for weak system-based coupling, the Boltzmann can be broken down at a low temperature because of the quantum correlation. And so a more rigorous way to study the probability of the system is to take the entire system plus bath Boltzmann probability and trace out the bath. The result is a thermally reduced density matrix. Now, this density matrix is not the same as the Boltzmann of a system unknown. Now, we ask two questions. First is how large is this difference? And the second is there any theory to describe this reduced density matrix? The answer, of course, is the Polaron-transformation. And here is one example. This is LH2 of the purple bacteria. Previously, Shorten's group have propagated the density matrix for a very long time. And they found that the non-time limit is not Boltzmann. So now we realize that this non-time limit is exactly the reduced density matrix. And here's the difference in the population. So even at a room temperature for such a highly biological system, the difference can be 20%. Therefore, one cannot ignore the system-based correlation, the quantum correlation, even for large molecules. Yeah. In addition to the difference in the population, there's also rotation in the basis set. The reduced density matrix is no longer diagonal in the eigenstate basis. So for spin, one can represent the basis as a vector on the block sphere. So now I have two vectors, one for the system Hamiltonian, the other is for the reduced density matrix. The difference between these two basis sets can be described by the theta, the deviation angle. So here we plot the deviation angle as a function of lambda, the reorganization energy. And indeed, as we increase the coupling strength, the deviation angle increases accordingly. And this represents a changeable basis set from eigenbasis to the side basis. The lower panel is more interesting. And here is the deviation angle as a function of temperature. And this is for very weak system-based coupling. So the result, at high temperature, we recover exactly the Boltzmann. That's a classical limit. But then, as we decrease the temperature, suddenly there's a dramatic deviation because the angle increases dramatically at a low temperature. So this again confirms the statement I made earlier that even for weak system-based coupling, the Boltzmann will break down at a low temperature. And this effect can be largely captured by the Polaron transformation. And here I use the spin boson as a model, as an example. So the Polaron transformation, in this case, is simply a displacement, a unitary transformation to displace the bass according to the electronic states. So B is the phonon displacement. After the Polaron transformation, the transformed Hamiltonian has a much weak tunneling matrix. So the tunneling term, delta, now reduces to kappa delta. Kappa is the renormalization constant, which is always smaller than 1. So the result, the tunneling is reduced. And the system-based coupling is also reduced. So this is completely based on the original work by Seogjoo and co-workers. And this rotational basis set also has implications on the dynamics. And here is the two limits that we all know. In the weak system-based coupling, then we can use the system-based interaction as a perturbation. Then the result will be the red field quantum mass equation. The non-time limit will be the Boltzmann in the eigenbasis. When the coupling is strong, then we can use the tunneling, the off-diagonal term, as a perturbation. The result will be the Neubauer, the non-interacting approximation. In fact, if you take the Markov limit, it becomes the Fermi-Golden rule rate. The non-time limit will be the Boltzmann in the local basis. Now, the Polaron transformation essentially rotates the basis from the eigenbasis to the local basis. Therefore, it can account for the system-based coupling from the weak to the strong. So using the Polaron basis, then we can apply the second order perturbation to derive the mass equation in the Polaron frame. And this is actually quite standard. The 3 speakers in this session also has done a lot of work in this mass equation. The form of a mass equation is actually very similar to the red field equation. There's some additional terms, but the rate is actually quite different. It's more complex. So I want to make 2 points about the Polaron mass equation. First is that this rate actually becomes the red field tensor in the weak coupling limit and reduces to the Fermi-Golden rule rate in the strong damping limit. Therefore, it bridges the 2 limits. Secondly, in the long time limit, the density matrix approaches the thermodynamic limit, which is defined by the Boltzmann in the exciton basis. That means the quantum mass equation is thermodynamically consistent. So this point are discussed in this review article. Now, with this Polaron approach, we studied various non-equilibrium process. So I will discuss in some details about heat transfer. And then in the last part of the talk, I'll briefly mention about the results on other applications, for example, quantum diffusion in organic semiconductors, quantum heat engine, and the phase interference. And these are papers we published in this area, and I This is a review article which sort of summarized all the results prior to 2016. So now I turn to the second part, which is heat transfer. Let me begin with a simple model, which was actually introduced by Seogjoo and Eitan, the non-equilibrium spin boson model. It's similar to spin boson model with two-level system, but now instead of one bath, it's coupled to two baths, one hot, one cold. The alpha is the coupling stress. The model has been studied in two limits. In the weak system bath coupling limit, one can use the red field equation and solve this exactly. In a strong coupling limit, there's a Neva solution. But in between, we have to use numerical calculations. So now, with the Polaron technique, in principle, we are able to find a closed form solution. But in order to do this, we first need to define the heat flux. In the weak coupling limit, one can use the Lindblad quantum mass equation. Then the flux is simply evaluated by the change of energy in the system. But this, of course, is perturbative. It applies only to the weak coupling. How do we define flux in the strong coupling? Well, our solution is to define the flux according to the rate of change in the bath. So instead of a system, we use bath. So this is the total energy change in the bath. That's a difference in the energy at time t, time 0. For the harmonic oscillator, it's simply the change in the occupation number. Now, how do we calculate that? We introduce the counting field. So this counting field will keep track of the occupation number of every mode in the bath. And then we have the generalized density matrix with the counting field. And this will be the Polaron mass equation with the counting field. And we call this non-equilibrium Polaron-transformed red field equation. At the long time limit, we have steady state. And this will be the moment generating function. By taking derivatives, we can get all the moments. Yeah. To leading order, the first moment is a steady state. And turns out one can actually obtain a closed form solution for the steady state. And here is the flux, the heat flux as a function of coupling, alpha system bath coupling strength. The red line, which is that the dashed line, is a red field solution. So it agrees perfectly in the weak coupling limit. The dotted dashed line is the strong, the Neva, which is for the strong coupling. And again, it agrees very well for large alpha. So our solution recovers the two limits and also predicts a turnover in between. So the heat flux becomes maximum at the intermediate coupling strength, which is alpha approximately equal to 1. The inserts also calculates the coherence, the off-diagonal density matrix elements. It shows that the coherence changes dramatically exactly at alpha. So the coherence will drop to 0 around the maximum. So in other words, in between the coherent and incoherent transition, the heat flux becomes maximum. Now we have a exact, we have the closed form solution. Now, how reliable is this solution? Well, we can compare with the numerical calculation. So we compare with a hierarchy calculation. The green curve is the numerical result. And the blue curve is the analytical solution. And so they have the same shape, and it agrees reasonably well. But as we decrease S is index here, then the agreement becomes worse because there's more slow modes. This was also discussed in the two previous talks. The one way to deal with this is to use the variational Polaron method, also by Bob Silby. But back then, Bob Silby did the single baths, one temperature. The problem here is that we have two baths. How can we use the variational method? For that, we have to define a partition function for non-equilibrium steady state. In other words, we have to define effective temperature for the system. Well, naively, we can actually define effective temperature by combining the left and the right baths. In other words, we fold the two baths into one bath. Formally, this actually can be done. The system bath coupling is completely described by the correlation function. And then we can add up the correlation function of the left and the right baths. But then this total bath is not really an equilibrium bath. It becomes equilibrium Gaussian bath under certain conditions. There are two possibilities, two conditions. One is the temperature difference between left and the right is small. Alternatively, at high temperature, classical limit. Then we can define effective temperature, which is the weighted average of temperature of the left and the right. Then we can apply the Bob Silby's variational principle and derive the non-equilibrium flux with this variational framework. So here's a comparison. Again, we use the first we use the super ohmic density. The blue curve is the standard Polaron transformation. The black curve is the variational Polaron. The green curve is the exact hierarchy calculation. So clearly, the variational method agrees much better with exact numerical calculation. Then we can also look at the ohmic spectral density. And here, the standard Polaron will not work. So we have to use the variational method. And also, the hierarchy is not very efficient for the ohmic. So we use the non-equilibrium green function method, another numerical method. And the symbols, the black symbols are the variational Polaron method. It agrees perfectly with the numerical result. The red curve, again, is the red field solution. The blue curve is the Fermi-Golden rule rate. And they agree in the two limits. Okay. Now we have been discussing the steady state. Well, steady state is actually the average. If we look at the current, it actually fluctuates with the time. So one way to describe this fluctuation is a variance. That's a fluctuation of the current. And according to Ahsan, there's a relation between the fluctuation of the current and heat conductivity. So in order to verify the Ahsan's relation, we need to evaluate the current to second order. And this actually can be done quite easily with the counting field. We just take second order derivatives. So that will be the closed form expression for the second order variance. Now we can compare the second order with the Ahsan prediction. So the symbols are the second order calculation in the Polaron frame, and the solid curve is the Ahsan prediction. They are on top of each other. However, this is only for small temperature difference. It's a 0.05. So in other words, the driving is very small. So now we increase the temperature difference to a larger value. Then the on-cycle prediction, the dashed line, will not be reliable anymore. But instead, there's another prediction based on the fluctuation theory. So I won't go through details, but that agrees perfectly with our calculation. And this also verifies that the Polaron transformation, the Polaron mass equation, is consistent with fluctuation theory. So the last part of the talk, I'll discuss a few applications and limitations of the Polaron approach. So I have 4 calculations. I have 2 slides for each calculation. So I may run over time, but I'll stop if my time runs out. Okay. And the first calculation is about quantum diffusion in a disordered system. So this will be a model for charge mobility and exciton diffusion in organic semiconductors. The model is very simple. First, we have the disordered tight bonding lattice with a side energy disorder. So this is essentially the Anderson model. So the dynamic disorder leads to the localization of the wave function. On top of that, we also have photon bath for each molecule. And because of coupling with photons, there's also dynamic localization. And the competition of the Anderson localization, dynamic localization, will dictate the transport. So here we use the Polaron-transformed Redfield equation to calculate the transport. So first we report the probability, so that's the spreading of the wave packet as a function of time. The left panel is for high temperature. At high temperature, we have a Gaussian profile. So that's the standard solution for random walk on the lattice, which is also diffusion. The right panel shows a low temperature. Interestingly, here is non-Gaussian. In particularly, there's a very sharp peak in the middle. So this is the inserts is the initial time equal to 2. So you can see more clearly there's a sharp peak in the middle, then a Gaussian profile. To understand this, let's take a simple picture of a polymer. Because of a conformational disorder, the wave function is broken down into segments. This is the Anderson localization. And initially, we have coherent ballistic motion within each segment. And that gives rise this peak. This peak actually has an exponential tail, and that's a signature of the Anderson wave functions. And then the thermal noise kick in and induce transitions between different segments. At a long time, we still recover normal diffusion. So eventually, as time increases, this peak will disappear and will recover the normal diffusion, but with the enhanced diffusion constant. Because now, instead of a step-by-step hopping, it hops by segments. Yeah. And here is the Polaron calculation of the diffusion constant as a function of temperature. So the low temperature will have a coherent band-like transport. At high temperature, we have incoherent hopping. And our calculation recovers the 2 limits and shows a turnover in between the 2 limits, so that we have a maximum diffusion constant at intermediate temperature. The lower panel shows the diffusion constant as a function of system-based coupling strengths, gamma. And here again, we also show the turnover. Above the turnover, the overdamped limit, we have a comparison with the Fermi golden rule rate. That's the dotted line. So clearly it agrees very well in a strong coupling limit. But then in a weak coupling, the Fermi golden rule underestimate diffusion constant because Fermi golden rule describes the side-to-side hopping. But here it's a hopping by segments. In a weak coupling, we can compare with a red field equation. That is the dash line. Again, it agrees very well for small alpha, small coupling strengths. But then as we increase alpha, the red field overestimate diffusion constant.
Jianshu, we are running out of time, so maybe you want to wrap it up.
All right, let me show one slice and then I'll wrap up. And we can also use this to study quantum heat engine. There's a very well-known limit over 3-level laser. I think Eitan actually knows this very well. There's a Carnot, actually the efficiency is bounded by the Carnot efficiency. But at that limit, the power is actually very small. So we want to understand what is the best performance. And for doing that, we need to tune the coupling. And again, we use the Polaron-transformation. And indeed, the optimal region is the intermediate region. So this is the region with the optimal efficiency, but optimal power. So let me stop here, and there's a few more slides. So overall, we show that the polaron can be applied to study non-equilibrium process. And I didn't discuss this. There's some difficulties to deal with the non-commutative coupling. So with this, I stop my talk. We'll be happy to answer any questions. Thank you.
So Seogjoo, do you want to have a few questions or do you want to continue and leave it for the discussion afterwards? Because we kind of are out of time.
Yeah, maybe 1 or 2 minutes. Yeah.
Okay, so I guess
you can ask yours. Yeah.
I can ask my question. So your definition of heat, okay, and also of Boltzmann distribution depends on how you break down the overall Hamiltonian to system, buff, and coupling.
Yes, yes.
This is not always unique. You can break the same Hamiltonian into different system, buff, coupling terms. So how does this affect your definitions of heat and of Boltzmann distribution?
Yeah, so that's a good point. And so to partially avoid this problem, we use we define the heat according to the bath. So we didn't use the system.
Yeah, but the buff Hamiltonian depends on how you break down the overall Hamiltonian into system, buff, and coupling. Doesn't that?
We have system-based coupling and system Hamiltonian, based Hamiltonian, but we use the best to define heat because the best energy is much
I understand. Okay, we can talk about this later. My point is that the breakdown into system buff and system buff coupling, as far as I know, is not always unique for a general.
It's not always unique because that term can be shifted to can be moved to the best part or can be moved to the.
And then how you define Boltzmann and how you define heat will also change with it, wouldn't it?
And there are some effects, but I think it's more reasonable for our calculation, it's more reasonable to use the definition of the bath. So that somehow can avoid the problem because the bath has much larger energy than the system-based coupling term. Okay.
Okay, so thank you very much for the speaker, for Jianshu. And I guess we are going to move on and to Sugi. Sugi, as you all know, okay, is from Queen's College in CUNY, and his title is Partially Polaron-Transformed Quantum Master Equation and Exciton Charge Transport Dynamics.
I'm really happy to talk after having organized many talks, and also I want to thank all the previous speakers who actually made my work much easier. I'm going to talk about partially Polaron-transformed quantum mass equation for exciton and charge transport dynamics. By the way, I am at Queens College at the Queens College of the City University of New York. And also, I also started some affiliation with the Korea Institute for Advanced Study as a visiting scholar this year. So the idea and concept of a polaron was developed a long time ago. So it dates back to Landau and Pekka, Borelli, and Holstein and Feynman. It was initially used a lot for describing rest charged states. And so if you have the any localized bare state, then they may be rather strongly coupled electronically. But if the environment becomes, dragged to each localized state, in other words, if each states become dressed by the environment, then the resulting electronic coupling becomes weakened. So the reason why that happens is that in addition to the bare electronic coupling, there are additional Frank-Condon overlap factors of two displaced operators, and that reduces the net electronic coupling. So this idea has been used a lot by Silve and co-workers for describing the excitation energy transfer, and also for developing unified treatment of incoherent and coherent dynamics. So when I was working with Bob Silve, so I heard a lot of these ideas. And at that time, I kind of felt that so many things have been done, and so there isn't that much left anymore. But later, when I started working as an independent researcher, I kind of realized that there is still one thing one can do, which is to incorporate the Polaron-transformed with more general quantum mass equation approach. So the idea is actually quite simple. The first step is to make Polaron transformation, which is system-dependent displacement of a harmonic oscillator beds. This is still unitary transformation in the total system plus bed space. So everything can be transformed accordingly. But then once you do that, you can redefine a small perturbation term. And then after that, you apply projection operator theory and maybe make perturbation approximation to obtain a practical time-dependent quantum mass equation. An important detail that one cannot overlook in this approach is that the initial condition and physical observable also have to be transformed accordingly, because if not, you are changing the nature of physical conditions and observables being measured. So we, along with many collaborators, I was able to develop a full second order time local Polaron-transformed quantum mass equation approach. First, in collaboration with Yuan-Chung, Cheng, David Reichman, and Joel Reeves in 2008. And after then, I completed the work by including all the effects of a coherent initial condition in 2009. And in 2011, this work was extended to multi-state system. And in 2012, actually, we extended the approach to non-Condon situations. Although this work has not been cited a lot, I think this is an important development. And in 2012, we also applied that to donor bridge acceptor system and then demonstrated some turnover behavior. And in 2019, I also worked on the distance dependence of the resonance energy transfer, including the Polaron-transformed quantum massification approach. So the whole approach was actually also described in a self-consistent way in chapter 9 of ultra-fast dynamics at the nanoscale book. And more recently, this is also described in my book on dynamics of molecular excitons. And also I should note that Yuan-Chung, Cheng, Ahsan, Nazir, and Jianshu Cao, and also many others that I couldn't cite here have also developed and worked on this idea, because I mean the idea itself is not really, I mean, something difficult to think about. It's just, I mean, so I think in that sense it has a lot of potential, and also it still can be developed further. Before I talk about the main topic, which is the partially polaron-transformed approach, let me talk about three previous works that I worked on. The first one is the non-condensed effect. So in the typical two-state system spin boson model, the coupling J is assumed to be independent of any degrees of freedom. However, if the two sides actually interacting, for example, with torsionally modulated electronic coupling, and also the torsional degree of freedom is also coupled to the environment, then you have to assume their dependence on the best degrees of freedom. So here, for example, you can assume that J depends on some variable phi, and the variable phi can be a linear combination of best degrees of freedom. In this case, the Polaron-transformed quantum massification approach actually can be extended. And here are some examples. So what you see is that the red dashed lines are without non-condensed effects. When you include non-condensed effects, depending on values of parameters, you see that there is more dephasing and also relaxation. But in this case, as you can see that the details of the amplitude and reference of the non-condensed effects actually make significant effect on the net dynamics. And we also worked on how the effective rate from Polaron-transformed approach compare with Redfield or super exchange limit and hopping dynamics. So this one shows that the Polaron approach nicely interpolates between the two limits. But more interestingly, the intermediate situation is pretty broad. And so what you can see is that the intermediate regime is quite broad, and also there is significant interplay of non-adiabatic effects and quantum coherence in this region. Finally, I also studied how the distance dependence of effective rate from the Polaron quantum mass equation deviates from the well-known 1/R6 dependence for purely transient dipole interactions. So these are dependence of the logarithmic rate with distance. You can see that at short distances, when the effect of when the electron coupling becomes larger, you can see significant effect of coherence. And this is when you multiply the rate with R to the 6. And what you see is that the enhancement due to the quantum coherence becomes significant only for fast and moderately coupled baths. And also the dependence is quite non-trivial. It is very complicated even in the simple model situation. And more recently, I've been studying applying the Polaron quantum master equation to multi-site situation like this. And what I find is that there is initial fast coherence transport that is pretty independent of the length. And also as the length becomes larger, the recurrence actually becomes smaller and smaller. So this actually shows that up to certain distance, without effect of disorder, definitely having longer grids can have positive effect if there is a contribution of quantum coherence. Okay, so far I have talked about interesting aspects of Polaron quantum master equation, but there are well-known issues with current version of second order Polaron-transformed quantum master equation. First of all, the Polaron transformation causes over-relaxation of some slow modes. So therefore, there is premature suppression of some coherence terms. And as a result, the equation becomes inaccurate for slow baths. So this actually has been well studied in, for example, a paper by Cao and co-workers. And there is no significant additional improvement for ohmic bath, and there can be also some problem with sub-ohmic baths. This is obvious because the divider Warlock factor vanishes in this limit. So there have been well-known methods to overcome this by former two speakers. One, for example, Ahsan Nazir and also Yuan-Chung Cheng. And also, as you just saw, Jianshu Cao's group also used a variational approach a lot for studying the steady state limit. So more generally, I became interested in this and then was wondering, without even assuming variational ansatz or any assumption a priori, whether we can actually develop a general framework of using partial Polaron transformation. And then after that, we can probably apply different approaches. And so based on that, I started working on this theory. So the idea of partial Polaron transformation is very simple. So given that you have this multi-site electronic Hamiltonian coupled to harmonic oscillator baths, we may apply Polaron transformation, but not the full one. We introduce frequency-dependent weighting factor. And the only requirement for the frequency-dependent weighting factor is that it decays like power law for small omega, and it becomes 1 for large omega. Then the Polaron transformed Hamiltonian can be written this way. Here I have subtracted this term and added into the zeroth order Hamiltonian. So these are all the detailed expressions for each energy and this displacement operator and divider factors. So at this point, we can define this as a zeroth order Hamiltonian for the system, and the whole can be defined as a zeroth order Hamiltonian for the dynamics. And this becomes the first order Hamiltonian. And then we can use this as the small Hamiltonian term and then apply the conventional projection operator technique. So for example, if we go to interaction picture of the zeroth order Hamiltonian and then apply this kind of a projection operator, then it's possible to derive formally exact partially Polaron-transformed quantum master equation for this reduced system density operator. And it has the same form as well-known one here, but it's important to keep the inhomogeneous term, as you can see here. And here, the definition of this interaction picture, the first order Liouville operator, I defined it this way. And here, this is the inhomogeneous term, the non-equilibrium contribution. This appears because we are changing the initial condition by applying the Polaron transformation. And then at this point, I should say that one can actually apply second order approximation, but it is possible to apply higher order hierarchy or generalized quantum master equation approach. So what I want to say here is that, in fact, Polaron transformation is not really, different from, it can be consistent with the other advanced approaches. Simply those things have not yet been developed. So I think someone actually can take this message and then work on these things, hopefully. And the same thing actually can be also transformed into time local form by well-known approach by Shibata and Arimichi in 1980. Then the time local equation becomes this form. And here, this actually backpropagates the total density operator and then project again. And then take inverse, then you get this time local form. So because of this term, the full exact time local form is even more difficult to solve compared to the time non-local form. But fortunately, at the second order, it becomes a well-known expression that can also be derived simply by using Von-Markov approximation. So the time local second order partially Polaron-transformed quantum master equation can be written this way. And this is the relaxation term. And because it's in the interaction picture, the other term, the inertial part, disappears here. We are only dealing with the relaxation part. And interesting thing is that now when you have this partial Polaron transformation, the bad collision part now has three different terms. And the first term is Polaron transformed part. And this is the untransformed part. And then you have to also deal with the cross terms. So these kinds of equations that actually can be seen in variational Polaron transformation. But what I'm saying here is that it's possible to actually derive general expressions for any kind of partial Polaron transformation. And also the inhomogeneous terms are also, they become more complicated. For example, this is a first order term, but even the first order term, we only need to calculate additional two Bath correlation functions. Even more interesting thing I find is that the second order inhomogeneous term, although it becomes more complicated, it still involves only the three equilibrium Bath correlation functions that have to be used for homogeneous relaxation term, plus this additional two terms that are needed for calculating the first order terms. So in terms of except that this partially Polaron transformed quantum master equation involves more terms, and also it is a bit more complicated. Essentially, it can be equivalent to fully Polaron transformed quantum master equation approach. So I started applying the equation to simplest possible situation. So the first thing I am trying now is two-level system coupled to the same type of local Bath. This is better known as a spin boson Hamiltonian without common modes. So in this case, the reduced zeroth order the renormalized zeroth order Hamiltonian becomes this one, and this becomes a first order term. And as you can see that the Bath average of this term becomes 0. And the result only involves, in this case, 3 Bath correlation functions that you see here. And in this case, because both state 1 and state 2 are coupled to the same kind of Bath, we only need to consider one kind of a Bath spectral density. So I wasn't able to complete all the coding, including inhomogeneous terms, but I was able to complete the calculation with only relaxation part. So I am happy to show some results. Here is the example for ohmic Bath. And this example is when I use a step function as the weighting function. What you see is that when omega h is very small, it becomes the fully relaxed, the Niba type of results. So in this case, there is no effect of coherence. And when omega h is very large, it approaches the simple second order time local Redfield type of approach. What you see is that when omega h is in between, actually it shows somewhere, I mean, the dynamics somewhere in between. So you can see that by tuning omega h, even in the simple case, you will be able to find the optimal coherence. Of course, in this case, it's at room temperature, and the electron coupling here is 300 wave number. And in this case, there is no contribution of the cross term, and you can see smooth transition between the two limits. The second thing is more interesting. So this is the case where I use this kind of function as a weighting function. And in this case, I have chosen omega h1, but changes the power in this weighting function. And what you see is that as omega, the power becomes larger, you see that it actually, the dynamics includes more coherence. And when alpha becomes 4, the coherence is even bigger than the step function form, meaning that the cross term actually makes non-trivial contribution. One has to be careful because the cross term, because of the cross term, the equation becomes unstable when alpha is equal to 1, in this case, for ohmic Bath. So alpha has become bigger than 1. And also what I find is that depending on the power of alpha, the possible value of omega, there is some kind of upper bound for the possible value of omega h. That is also because of the cross term. So with this, let me summarize. What I showed in this talk is that I have developed a general partially Polaron-transformed quantum mass equation that is applicable now to both exciton and charge transport dynamics for any spectral density and for any initial condition. And the weighting function and its parameters can be used to find the best second order approximation. So maybe through variational optimization, or maybe through machine learning approach comparing to various benchmark calculations. I believe that this has particular important application for polarity dynamics. And as a next project, I plan to extend this to time-dependent Polaron transformation approach. And I think this is feasible. I want to thank my group members, especially Lei Yang, and also many collaborators, and especially Tim Merkelva, Reichman, and Joel and Yuan-Chung, and the late Bob Silvey, and also thank the support of many others. Thank you. So this is my end of my talk. So I'm happy to answer any questions.
Thank you, Suli. So there are two questions. So I will start with the second one. How do you choose a sensible value of omega h and alpha in the cutoff?
I don't know at this point. Yeah, so the idea is that without choosing them, you can actually derive closed form expressions. And then now the outcomes of those calculations for different values of an omega h and alpha can be actually be used for determining the optimum function for weighting function and also alpha and omega h. I mean, honestly, I have some ideas about how to choose. So it's possible to guess, but it's not possible to say definitely because it depends on the physical situation and depends on the type of spectral density.
Thank you. Going with my question, I guess. So this is a general question actually to all the speakers maybe, but I'll ask you because, okay, you've done a lot of work on this. So does Polaron-transformed quantum master equation, seem to focus mostly on, harmonic Buff Hamiltonian kind of situation, even though people have said that you can generalize, but most of what we've seen is based on that. And then, of course, you are competing against methods like, Heisenberg equation of motion, okay, MCTDH, QAPI, that can also do those numerically exact, supposedly. So can you somebody comment about the computational pros and cons, okay, of those methods? I mean, why would you use Polaron-transformed, which are approximate, and not just the exact, numerical methods for those kinds of systems?
Yeah, let me actually answer the question first. I think actually now that you have the partially Polaron-transformed quantum master equation approach, it actually opens the possibility more easily of applying the Polaron transformation with more general path, because now the untransformed part can be also the anharmonic path. Of course, if you try to do Polaron transformation for anharmonic degrees of freedom, you can do for certain simple model systems, but that will be more mathematically involved.
And what about the computational part of it? Okay, is it beneficial computationally to do this compared to the numerically exact methods?
Well, I think it's always in details. Yeah.
Yeah, but in your experience and other experience, okay, how does this?
Yeah, maybe Jianshu can answer.
Maybe just comment on this. For our calculation of a one-dimensional chain, it will be impossible to do hierarchy because there's hundreds of states, hundreds of paths, or any other numerical method for that sake.
So how does this scale, okay, in terms of the size of the system?
So, Eitan, why don't I stop recording, okay? And
yeah, we can move to the discussion, I guess.
Yeah, so anyway, so I want to thank you all of you for attending this, and this is the end of the official workshop. Thank you.